Welcome to qnawire.
That in the isothermic expansion in a Carnot cycle, we're going to have the 3 moles of an ideal gas are going to have initially a volume equal to 0.035, so 350 cubic meters. We know that the temperature is going to be equal to 430 Kelvin. So upon expansion, the value for the pressure is going to be half. That means that the final pressure is going to be equal to 1/2 of the initial pressure. This implies that the final volume needs to be equal to 2 times the initial volume. So over here, since we are going to have an ideal gas, we know that the change of internal energy is going to be equal to 0 because we have an isothermal expansion. This is because the internal energy for an ideal gas is only a function of the temperature of the system. So over here, first of all, in part A, we want to know what is going to be the final volume of the gas. And as I mentioned, it is going to be double the initial volume. So the final volume would be equal to 0.0700 cubic meters. For B, we need to find the work done by the gas, and in this case, the work is going to be given by minus the integral for initial volume to final volume of pressure differential of volume. This is going to be equal, replacing the value for pressure in ideal gas law, which is nRT divided by B, would be equal to minus nRT logarithm of final volume over initial volume. In this case, since the final volume is double, we will get minus nRT logarithm of 2. Replacing the values, we're going to have 3 mole multiplied by 8.314 joule per mole Kelvin times 430 Kelvin times logarithm of 2. So we're going to end up with 7,434 joules of work with a negative sign in front of it. In this case, since delta U is equal to 0, that means that Q plus W is equals to 0. So the heat for this process would correspond to 7,434 joules. Okay, so we have found the work done in part B, and for part C, we're told that we need to find the change of entropy. In this case, the change of entropy would correspond to the reversible heat divided by the temperature at which this occurred. In this case, the heat for the reversible process in which we're dealing with this thermal expansion, we're going to get 7,434 joules divided by the temperature, which is 430 Kelvin, which gives us 17.288 joules per Kelvin. And finally, for part D, if the heat exhausted by the engine in one cycle is going to be equal to 4.50 times 10 to the 3 joules, then what is going to be the efficiency for the cycle? So in this case, to find the efficiency, since we're told that 4.5 times 10 to the 3 joules was exhausted from the system, in order to know the efficiency, we're going to take is the value for the heat corresponding to the reversible process, which is 7,400. The heat for the reversible process would be our denominator, 7,434 joules, and the heat exhausted is going to correspond to the work that is going to be produced by the cycle for the overall cycle. Okay? So this is going to be because, due to conservation of energy, the heat would be equal to Q, the net heat transfer, and this would be equal to, normally when you have your Carnot cycle, it would be heat coming from the hot reservoir minus heat coming from the cold reservoir. So in this case, 4.5 times 10 to the 3 joules. This is going to give us an efficiency of 0.6605, which is around 60.5%. And with that, it would be all. Thank you very much, and have a good one.